Okay, so non-steady state diffusion is our topic today. This is different than our steady state diffusion equation, which showed that the concentration difference between a known amount of, say, zinc on the surface of a penny versus what was on the other side of that penny would have a very predictable and linear concentration gradient of zinc within that penny. So that was a steady state condition. In non-steady state scenarios, we will see that the concentration of that diffusing species, going back to our penny idea, this would be the zinc, is a function of both time and position. So previously, time was not in our profiles across a boundary of material. It was simply the distance x through that boundary of material that we looked at for the concentration of that diffusing species. But now we see that the concentration at the diffusing species is a function of both position and time. Okay. And so this is Fick's second law relative to our previous content, which was Fick's first law. So Fick's second law is shown down below here. It could be a little intimidating to look at first, so let's kind of read it out at first, and that's sort of scripted for you here. So it tells us that the change in concentration with respect to time, that's the left-hand side, is equal to the diffusion constant, which is still a constant, specific to conditions like temperature and materials. Okay, so let me say that all again. Change in concentration with respect to time is equal to the diffusion constant multiplied by the second derivative of the concentration with respect to position x. So hopefully you can see here that the left-hand side has some dependence on time and a component of the right-hand side has some dependence on the position. And we're using a second derivative here to pull out the slope and the rate of change of concentration with x. And that is where partial derivative mathematics are needed, and that is something that we are not going to have you do for this course, but simply apply one of the solutions per the conditions that I mentioned a moment ago. Okay, so let's take a look at this, and we'll constantly remind ourselves of the zinc-copper scenario. So this sort of bar here in gray might be the cross-section. So this is therefore the surface of the top surface of the copper penny in our scenario, and this is moving deeper and deeper and deeper into the copper in cross-section a long ways until we get to the bottom face of that copper penny. Okay, so the sort of orange spheres here represent our zinc layer on the top, and our gray skinny bar here represents a simple skinny cross-section of that copper penny. Okay, we're going to rely on understanding that the surface concentration of zinc atoms in this case is labeled as concentration CS. So this is what we said does not change over infinite time for the experiment. So we're going to assume that there's always a supply of zinc atoms and that the concentration there is constant at value CS. Okay, so reminding ourselves of the steady state diffusion that we've looked at, we saw that the position x here between, say, the boundaries of the material, so position x is going from x equals 0, that might be the surface of the penny, through to perhaps the end of the penny, shown here. And we saw that the concentration gradient was linear when we had a steady state diffusion. Okay, so that's a linear trend in the concentration of zinc from the area of high concentration of zinc on the outside and starting at high values of zinc in the copper and working its way down to lower and lower values, ultimately to the lowest value, which is labeled here as concentration naught. So that is that could be a concentration value that is non-zero or it could be a concentration value that is exactly 0. Depends on the problem. Okay, so that is steady state kind of diffusion as we've tackled it before. Now let's see what non-steady state conditions do to our problems here. Okay, so let me just clean up some of this. Okay, so we want to watch this profile now as it might change with temperature, or time. So early on, at time t equals 0, this is the moment before any diffusion has occurred, we have no concentration of the diffusing species, zinc for us in this analogy. None of it is in our penny, and it doesn't matter how deep we go into that penny, that concentration value is the same, okay? So it stays equivalent to C naught, provided we haven't done any diffusion, we've only got the zinc on the surface. At some time later, T1, we will start to see some of that zinc in the copper. So as we go from the topmost surface, we're going to see some zinc content that is close to CS, but not exceeding it. And of course, zinc at the surface is still at its original concentration. As we move deeper and deeper into the penny, that concentration of zinc that has diffused in is dropping as a function of the position. So that is the dependence on position idea there. Now, as we move to a different time period, to time T2, we can see that the concentration gradient is different now. So that is now the at time T2 being greater than T1, we have concentration values that are higher than they were as a function of that same position in the time T1. Okay. Notice again that concentration in the penny never exceeds the CS value, and that the CS value is still assumed to be constant for this story. Okay, and then T3, same idea there. Sometime later, and T3 being greater than T2, being greater than T1, and of course greater than the moment it all started, T0, we have a concentration gradient that is showing higher data for those same X positions. So clearly time is giving us a different concentration gradient, giving us more evidence of that diffusion species, zinc, into our copper. And we are approaching the linear scenario here, where the supply and loss of zinc from the surface to the exterior would be at a steady rate, so therefore a steady state diffusion condition. Okay. Now, some of you might know the composition of coins and other kind of copper-based materials, and so zinc might already exist in the copper at time t equals 0. So that would be a condition where C naught would have a non-zero value, and we would apply the same ideas that we have just said, but assuming that we're talking about new zinc atoms into that already zinc-containing copper. Okay, so that's how we distinguish from that second scenario. Okay, so having said all that, clean up some of the slides so we can read some of these other things now. We can see here that these concentration gradients are curved, and with time they're approaching that of the steady state condition. Okay, some of these ideas I've said here. I've used the term new zinc to indicate that we're diffusing zinc from the outer surface of the copper into the copper that might already have a little bit of zinc from previous history, previous processing. Okay. And so we see those sort of statements there about how the concentration profiles change between T equals 0, the moment before a single atom goes into the copper slab, versus T1 a little later, T2 a little later still, and T3 later even still. Okay. And so as we've noticed here, as time proceeds, these concentration gradients approach the condition that we've seen before for steady state diffusion, and where the mathematics are a little easier, but we can still handle these non-steady state conditions. which are speaking to pre-equilibrium conditions. Pre-equilibrium conditions would be where the sort of rate of copper into the material would maybe match the rate out of the penny, for example. And we would have a nice steady state profile in the concentration gradient there.